All right, so get ready, because today we're going to dive deep into the world of machine learning.
Sounds good.
You sent over a ton of notes and excerpts, and it looks like you're really into linear regression, classification, and decision trees. So we're here to kind of help you go through all of it and find the good stuff and leave you feeling like you've really learned something about these tools.
Yeah, it's a really great selection of material. And it seems like you are particularly interested in how these algorithms can be used to predict things.
Right.
Like continuous values, like stock prices, housing costs, or to classify things into different categories, like spam versus legitimate emails.
Okay, so let's just start with linear regression.
Okay.
Because that seems to be kind of where your notes begin. And I remember struggling with this one in school.
Yeah.
But the way you've laid out all the graphs and diagrams here, it's actually starting to make sense.
Visualizing it definitely helps.
Yeah.
At its core, linear regression is all about finding the best fitting straight line through a set of data points.
Okay. You're trying to find the line that minimizes the distance between the line itself and all those data points that are scattered around it.
Right, so it's like finding the average trend in the data, but instead of just a single number, we get this whole line that shows the relationship between all the different variables.
Exactly. And the beauty of it is once you have that line, you can use it to predict the output for any new input.
Okay.
So if you know the square footage of a house,
Right.
you could use a linear regression model to predict its price.
That's pretty cool. But how do we actually find that best fit line?
Right.
The notes mention something called the normal equation.
Yes.
And it looks kind of intimidating with all those matrices.
I hear you.
Yeah.
Matrix math can definitely be a bit daunting.
Yeah.
But the normal equation is actually a pretty elegant solution.
Okay.
It uses a matrix operation called the pseudo-inverse to directly calculate the optimal weights for your line.
Pseudo-inverse, that sounds complicated.
It might sound fancy, but think of it as a way to invert a matrix, even if it's not perfectly square.
And this inversion allows us to solve for those weights that define the slope and the intercept of our best fit line.
Okay, I think I'm starting to get it.
Good.
But the notes also mention gradient descent as a way to find this best fit line.
Yes.
Is that just another way to do the same thing?
It is another method, and it's particularly useful when you have massive data sets.
Gotcha.
Gradient descent is an iterative process. It starts with an initial guess for the line, and then repeatedly adjusts the weights, taking small steps down the slope of what's called the error function until it reaches the minimum.
So it's like if a hiker is trying to find the lowest point in a valley by just taking small steps downhill?
Exactly. And just like a hiker can adjust their step size,
All right.
we can control something called the learning rate in gradient descent to determine how quickly we converge on that minimum error.
That makes sense. The notes even mention something called stochastic gradient descent. Is that like a super fast version of gradient descent?
You could say that stochastic gradient descent. Right. Or SGD.
SGD updates the weights based on a small random sample of the data rather than the entire data set at once.
Okay.
And this makes it much faster, especially when you're dealing with millions or even billions of data points.
So it's like taking shortcuts through the valley instead of following the most gradual path down.
Exactly. And in practice, SGD converges to a good solution much faster than traditional gradient descent,
Wow.
making it very popular.
Okay, so we've got these methods for finding the best fit line.
Yes.
But I'm wondering, can we use linear regression for classification?
Okay.
Could we just draw a line and say everything on one side is one category and everything on the other side is in another category?
That's a logical thought, and it might seem like it would work.
Yeah.
But using linear regression for classification has a major pitfall.
Okay.
It's way too sensitive to what are called outliers, those data points that stray far from the typical pattern. Ah, I see what you mean. The notes actually had a diagram that shows how an outlier can really skew the entire line and mess up the classification.
Exactly.
So what's a better approach then for classification?
Well, that brings us to k-nearest neighbors.
Okay.
Or KNN.
KNN.
Imagine you're trying to figure out what kind of fruit a new one is based on its size and color.
Okay.
With KNN, you would look at the k nearest fruits in your data set, and you'd let them vote on the classification of the new fruit.
So if we set K to 3, we'd look at the 3 fruits that are most similar to our new fruit.
Exactly.
See which category they belong to.
Yes.
Whichever category has the most votes wins.
Precisely. And just like in a real election, choosing the right number of voters, that K value is crucial.
Right.
If K is too small, then a single outlier could sway the vote.
Right.
But if K is too large, we might oversimplify things and miss subtle distinctions between categories.
Right. It's like that Goldilocks problem. We need to find the just right value for K.
Exactly. And the diagrams in your notes show how different K values affect that classification boundary.
Okay.
With a small k, the boundary is very sensitive to individual data points and results in a really jagged and complex boundary. But with a large k, the boundary becomes much smoother and more generalized.
So finding the optimal K is all about finding that balance between being sensitive enough but not too generalized?
Yes.
Seems like that would be a lot of trial and error.
You're getting it. And there's a technique called cross-validation that helps us systematically test different K values and choose the one that performs best on unseen data.
So we're not just hoping for the best.
Right. We'll get into the details of cross-validation a bit later. But for now, just think of it as a way to make sure our model isn't just memorizing the training data,
Gotcha.
but can actually generalize to new examples.
That makes sense. But are there any limitations to KNN? It seems almost too simple and intuitive.
Well, one limitation is that it can be computationally expensive,
Okay.
especially with large data sets.
Right.
Imagine having to compare a new data point to every single data point in a data set with millions of examples. That can take a lot of processing power.
Yeah, I can see how that would be a problem.
So it's not exactly a silver bullet for classification.
Right.
Are there other approaches that might be more efficient?
Yeah, I'm curious.
Absolutely. That leads us to decision trees,
Okay.
a powerful and versatile algorithm that's really well suited for handling large data sets.
All right.
Think of a decision tree like a flowchart with a series of yes or no questions that lead to different outcomes.
Okay, I'm picturing it.
Good.
So we ask the question about the data, and depending on the answer,
Right.
we branch off in different directions
Exactly.
until we reach some final classification.
You nailed it. And the key to building an effective decision tree lies in choosing the right questions at each step.
Okay.
We want questions that effectively split the data into what are called more homogeneous subsets, meaning groups where the data points all belong to the same category.
So we're trying to divide and conquer the data. Yes. Separating the apples from the oranges.
That's a great way to put it. And to measure how pure or homogeneous those subsets are, we use a concept called impurity.
Okay.
The lower the impurity, the better the split.
This is starting to get interesting.
Good.
But how do we quantify impurity? Is there some mathematical formula for that?
There are actually several different measures of impurity, but one that is commonly used is entropy.
Entropy. Okay.
Think of entropy as a measure of disorder or randomness.
Okay.
A high entropy means that there's a lot of mixing between categories,
Right.
while a low entropy means things are nicely separated.
So we want to find questions that lead to splits with low entropy.
Exactly. And to guide us in choosing the best questions, we use a concept called information gain.
Okay.
It basically tells us how much a particular question reduces the entropy or the disorder of the data.
So we're looking for questions that give us the biggest information gain.
You got it. It's like playing a game of 20 questions. But instead of trying to guess a specific object, we're trying to categorize all the data points.
Right.
And by choosing questions strategically,
Yeah.
based on information gain,
Right.
we can build a decision tree that efficiently sorts the data into its rightful categories.
Yeah, this is really cool.
Good. I'm glad you're following along.
So decision trees are kind of like building a roadmap through the data with all these carefully chosen questions.
Yeah.
It's a really cool way to visualize how the classification happens, especially compared to KNN,
Right.
where it seems like we're just comparing everything to everything else.
Yeah.
Speaking of KNN, you mentioned cross-validation earlier.
Yes.
And I'm curious to understand how that actually works.
Okay, great question.
Yeah.
Cross-validation is a technique that we use to evaluate how well our models will perform on data that they haven't seen before. It's like a dress rehearsal before the big performance.
Okay, I like that analogy.
Yeah.
So how do we set up this dress rehearsal for machine learning?
Imagine you have a cake, and you want to make sure that everyone gets a fair slice to taste it.
Okay.
With cross-validation, you divide your data into several folds or slices.
So instead of just using all our data to train the model, we're splitting it up.
Exactly.
Okay.
Let's say we choose 5 folds.
Right.
We would train our model on 4 of those folds and use the remaining fold to test its performance.
Right.
And then we would repeat this process 5 times,
Okay.
each time using a different fold for testing.
So it's kind of like we're rotating who gets to taste the cake so that every part of the data gets a chance to be in the test set.
That's a great way to think about it. And by averaging the performance across all 5 folds,
Right.
we get a much more reliable estimate of how well our model will generalize to new data.
This is making a lot more sense.
Good.
So we can use this cross-validation to fine-tune that K value in KNN,
Right.
or even compare different algorithms altogether.
Exactly. It's a really versatile tool that helps us choose the best model for whatever task we're working on.
Now back to decision trees for a moment. We talked about entropy and information gain.
Right.
But my notes also mentioned something called the Gini impurity.
Yes.
Is that just another way to measure how pure the data is after a split?
It is.
Okay.
The Gini impurity is another popular way to measure impurity.
Okay.
It calculates the probability of misclassifying a randomly chosen data point from a given set.
So a lower Gini impurity means we're less likely to make a mistake in our classification.
Exactly. And in practice,
Yeah.
both entropy and the Gini impurity often lead to very similar decision trees.
Okay.
So it often comes down to personal preference or just computational efficiency,
Gotcha.
whichever one you end up choosing.
Now, my notes also mentioned some other terms related to decision trees, like pruning and overfitting.
Right.
Can you explain what those are all about?
Of course. Overfitting is a very common problem that we see in machine learning,
Okay.
where a model learns the training data too well, almost memorizing it,
Yeah.
and as a result, it performs poorly on new, unseen data. It's like a student who crams for a test, and they can answer all of the practice questions perfectly,
Right.
but then they fail the actual exam
Yeah.
because they didn't really grasp the underlying concepts.
So it's like the model is too focused on the specifics of the training data
Yes.
and can't really adapt to new situations.
Exactly. And with decision trees, overfitting can happen when we allow the tree to grow too deep and complex.
Okay.
It might perfectly classify the training data,
Right.
but it becomes too specialized and loses its ability to generalize.
So how do we stop this overfitting from happening? Is that where pruning comes in?
You got it. Pruning is a technique that we use to simplify the decision tree
Okay.
by removing branches that don't contribute very much to the overall accuracy.
Okay.
It's like trimming away excess leaves and branches to create a much healthier and more resilient tree.
So we're finding that balance between being complex enough to capture the data,
Right.
but not so complex that it becomes too speculative.
Precisely. And there are different approaches to pruning,
Okay.
such as what's called pre-pruning,
Pre-pruning.
where we stop the tree from growing beyond a certain depth,
Gotcha.
or post-pruning, where we grow the full tree and then remove the branches later based on some criteria.
It seems like there's a real art to finding the right decision tree for each problem.
Yeah, that's true. It often involves experimenting, trying different pruning techniques, and evaluating their performance using that cross-validation that we talked about earlier.
This is really fascinating.
Good. Glad you think so.
I feel like I'm starting to see the bigger picture of how all of these algorithms work
Yes.
and how we can tune them to get the best performance.
That's great to hear. And speaking of fine-tuning,
Yes.
let's circle back to linear regression for a moment.
Okay.
Earlier, we talked about how outliers can skew the best fit line, potentially leading to inaccurate predictions.
Right.
Are there techniques we can use to mitigate the impact of those outliers?
That's a good question. My notes mention something called regularization, but I'm not sure what that means.
Okay, regularization is a technique that we can use to prevent overfitting
Okay.
by adding a penalty to the complexity of the model.
Mm-hmm.
It's like adding a bit of resistance to the line fitting process,
Okay.
preventing it from bending and twisting too much to accommodate those outlier points.
So instead of chasing after every single data point,
Yes.
including those outliers,
Right.
we're encouraging the model to find a more general trend.
Exactly. And there are two common types of regularization: ridge regression and lasso regression.
Okay, so ridge regression, what's that all about?
Ridge regression adds a penalty to the sum of the squared weights of the model.
Okay.
And this penalty essentially shrinks the weights, pushing them closer to zero.
So it's like applying a little bit of force that's pulling the weights towards the center
Yes.
and preventing any single one from becoming too dominant.
That's a great way to think about it.
Okay.
The strength of this penalty is actually controlled by a parameter called lambda.
Lambda.
A
Yeah.
larger lambda leads to more shrinkage, resulting in a simpler model.
And what about lasso regression? How's that different?
Lasso regression, instead of squaring the weights,
Okay.
it adds a penalty to the sum of the absolute values of the weights.
Okay.
This penalty can actually force some of the weights to become exactly zero,
Wow.
effectively performing what's called feature selection.
So not only is it preventing overfitting, it's helping us identify the most important features.
Exactly. It's like Lasso saying, hey, these features are really important. Let's focus on those.
Okay.
These other features, they're just adding noise. Let's get rid of them.
This is incredible.
Yeah.
So regularization gives us all this control over how complex our models are.
Yeah.
And it helps us balance that accuracy and generalization.
Yes, it's a very valuable tool to have.
Now, shifting gears a bit.
Yeah.
You mentioned earlier that there are two main categories of machine learning models.
Yeah.
Generative and discriminative.
Yes.
I remember seeing something about this in the notes,
Mm-hmm.
but I'm a little fuzzy on the differences between them.
Okay.
Could you remind me?
Of course.
Okay.
Think of it this way. Generative models try to learn the underlying process that generated the data,
Okay.
while discriminative models focus on just separating the data into different categories.
Right.
It's like the difference between understanding how a cake is baked
Yeah.
versus just being able to tell a chocolate cake from a vanilla cake.
I see. Okay.
Generative models are all about understanding the how and the why,
Yeah.
while discriminative models are much more pragmatic and focus on the what.
So generative models are the storytellers, and the discriminative models are more like the detectives.
I love that analogy. And depending on your task,
Right.
you might choose one approach over the other.
Okay.
If you're interested in understanding the underlying processes that generated the data,
Yeah.
then a generative model might be a good choice.
Okay.
But if your main goal is just to accurately classify new data points,
Right.
a discriminative model might be more efficient.
This is really helping me to see the bigger picture
To
of how all these different types of models fit together.
give you a concrete example of a generative model, let's dive into naive Bayes.
Okay.
It's a surprisingly effective algorithm,
Right?
especially when you have lots of features, but maybe not a lot of data to work with.
Naive Bayes, the name sounds almost like a contradiction.
Right.
How can something be both naive and effective at the same time?
That's the beauty of it.
Yeah.
Naive Bayes makes a simplifying assumption that all the features are independent of each other,
Yeah.
given the class label.
Okay.
It's like saying, knowing someone's favorite color doesn't tell us anything about their height,
Right.
even though in reality there might be some subtle correlations there.
So it's naive because it's ignoring those potential relationships between the features.
Exactly. But surprisingly,
Okay.
even with this simplifying assumption,
Right.
naive Bayes often performs remarkably well in practice,
Wow.
especially with tasks like text classification, like spam filtering.
Interesting. But how does it actually work? My notes mention Bayes' theorem, but I haven't really thought about probability theory in a long time.
No worries. We'll take it step by step.
Okay.
Bayes' theorem is a way to update our beliefs about an event based on new evidence.
Okay.
In the context of naive Bayes, we're trying to calculate the probability of a data point belonging to a certain category,
Okay.
given its features.
Right.
So we're essentially asking, given that we know these things about this email, the sender, subject line, the words it contains, what's the probability that it's spam?
That makes sense.
Good.
Okay. I think I get that part.
Okay.
But how does that naive assumption about the features being independent come to play?
That assumption allows us to simplify the calculations that are involved in applying Bayes' theorem.
Okay.
Instead of having to consider all of the complex interactions between features,
Yeah.
we can just treat each feature as if it contributes independently to the probability of the class label.
So we're breaking down the problem into smaller pieces.
Exactly. And this simplification makes naive Bayes very computationally efficient,
Right.
especially when we're working with what's called high-dimensional data with lots of features.
That makes sense.
Yeah.
What about situations where we see a feature in a new data point that we've never seen in our training data? Wouldn't that throw off the calculation?
That's a great question.
Yeah.
And that's where a technique called Laplace smoothing comes in.
Okay.
It essentially adds a small constant to our counts to prevent any zero probabilities
Okay.
and ensures that our model can handle those unseen features gracefully.
So it's like we're adding a little bit of flexibility into our probabilities and
think-
preventing them from becoming too rigid.
Yes, it helps our model be much more robust and adaptable
Okay.
to new situations.
This has been really helpful. I'm starting to really understand naive Bayes and how we can use it.
Good.
Now, my notes mention a specific type of naive Bayes called Gaussian naive Bayes.
Right.
Is that just a specialized version for handling continuous data?
That's right. Gaussian naive Bayes is specifically designed for data sets where the features are continuous, meaning they can take on any value within a given range.
So instead of categories, we're now dealing with distributions.
Exactly. And Gaussian naive Bayes assumes that those continuous features follow a normal distribution,
Okay.
which is also known as a Gaussian distribution or a bell curve.
So we're assuming something about the shape of the data.
Precisely. And this assumption allows us to use the properties of the normal distribution to calculate the probabilities that we need for Bayes' theorem.
Okay, I think I'm following.
Good.
My notes also mention covariance matrices in the context of Gaussian naive Bayes.
Yes.
And honestly, that's still kind of confusing for me.
No worries. Covariance matrices can definitely be tricky.
Yeah.
Think of a covariance matrix as a way to capture the relationships between different features.
Okay.
It tells us how much two features tend to vary together.
So if two features have a high covariance,
Yes.
it means they tend to move in the same direction.
Exactly.
Okay.
And if they have a negative covariance,
Yeah.
it means they tend to move in opposite directions.
Got it. Okay.
So the covariance matrix tells us how these features are related to each other.
But how do covariance matrices play into Gaussian naive Bayes?
Well, in Gaussian naive Bayes, we need to estimate the mean and variance of each feature for each class.
Okay.
And the covariance matrix comes in when we calculate the likelihood of observing a particular data point
Right.
given a certain class.
So it helps us to account for the relationships between those features when we're trying to classify something new.
Exactly. And different assumptions about the covariance matrix actually lead to different decision boundaries between those classes.
Interesting. So the way we deal with the covariance matrix can actually affect how well our model works.
Absolutely. There are different variants of Gaussian naive Bayes that make different assumptions about that covariance matrix.
Gotcha.
For example, one variant might assume that all features have the same variance,
Okay.
while another variant might allow each feature to have its own unique variance.
So there's a lot of different options and flexibility within Gaussian naive Bayes.
That's true. And choosing the right variant often involves some experimentation
Right.
and evaluating how well it performs on your particular data set.
This has been a really good discussion.
I'm glad to hear it.
I feel like I've gone from being intimidated by these algorithms
Yeah.
to actually understanding how they work and how I might choose the right one for a problem.
That's fantastic. And remember, we've really only just scratched the surface here.
Right.
There's a whole world of machine learning algorithms out there,
Yeah.
each with its own strengths and weaknesses.
I can imagine.
It's like having a giant toolbox full
Yeah.
of specialized tools for different tasks.
Wow, it feels like we've covered so much.
Yeah.
From linear regression to k-nearest neighbors, decision trees, and even naive Bayes.
Yeah, a lot of ground covered.
It's amazing how these algorithms can find patterns in the data.
And we've only just scratched the surface, really.
I know it's a lot.
There's a whole universe of machine learning algorithms out there,
Right.
each with its own strengths and weaknesses.
Yeah.
It really is like a giant toolbox
Right.
with all these specialized tools for all different kinds of tasks.
So how do you even choose the right tool? It seems really overwhelming.
Right. Well, that's where experience comes in
Okay.
and a deep understanding of the problem that you're actually trying to solve.
Right.
It's a bit like being a detective.
Okay.
You gather clues, you analyze the evidence,
Right.
and you choose the tools and techniques that are most likely to lead you to the solution.
So there's no one perfect algorithm for everything.
Not exactly, but there are some general guidelines, of course.
Okay.
Like, for example, if you're dealing with a classification problem that has a lot of features, but maybe you don't have a ton of data,
Yeah.
then naive Bayes might be a good place to start.
Okay.
But ultimately, the best approach is to experiment, try different algorithms, and see what works best for your specific data and the task at hand.
It's all about finding that balance between the model's complexity and how well it works on new data.
Exactly. And that brings us to a really fundamental concept in machine learning. It's called the bias-variance trade-off.
Okay, bias-variance trade-off. I feel like I've heard that before, but I need a little reminder about what it means.
All right. Think of bias as the error that's introduced by approximating a real-world problem, which can be very complex, with a simpler model.
Right.
A highly biased model oversimplifies things and misses those subtle nuances in the data.
So it's like trying to fit a straight line to a data set that's actually curved.
Exactly.
Okay.
Now, variance, on the other hand, refers to how much the model's predictions actually change
Okay.
based on those small fluctuations that we see in the training data.
Okay.
A model that has high variance
Yeah.
is very sensitive to noise
Right.
and might overfit to the training data, performing poorly on new examples.
So it's memorize the training data instead of learning the actual patterns.
Exactly.
All right, so we need to find that middle ground.
Yeah, the key is to find that sweet spot, that balance between bias and variance.
Okay.
We want a model that's complex enough to capture the essential patterns,
Hmm.
but not so complex that it becomes overly sensitive to noise and overfits the training set.
It's like choosing the right amount of detail for a map.
I like that. A
Yeah.
great analogy.
Enough detail to be helpful,
Right.
but not too much that it's overwhelming.
Exactly. And understanding that trade-off is crucial for choosing the right algorithm, tuning its parameters,
Right.
and evaluating its performance.
It seems like everything we've talked about comes back to this idea of balance.
Yes.
Simplicity versus complexity, accuracy versus generalization, bias versus variance.
It's all connected. It
Yeah.
is. It's a beautiful tapestry.
It is.
And as you continue exploring machine learning, you'll find those themes popping up everywhere.
Now, we've talked a lot about the algorithms, but
Yeah.
what about the practical applications for all of this?
Well, applications are practically limitless. Machine learning is being used everywhere, from healthcare and finance to transportation and entertainment.
Wow.
Like in healthcare, it's used to diagnose diseases, personalize treatment plans,
All right.
and even speed up drug discovery.
That's pretty amazing.
Yeah, and in finance, it helps to detect fraud, assess risk, and optimize investment strategies.
Okay, so it's really changing all these different industries.
It is. It's like we're watching a technological revolution unfold.
Yeah.
And this is just the beginning.
Really?
As we generate more and more data and these algorithms become even more sophisticated, the potential for machine learning is huge.
So for someone just getting started in machine learning, where would you recommend they focus?
Well, a strong foundation in math and statistics is key.
Okay.
In programming.
Right.
But it's also really important to think critically, ask the right questions, and be able to translate those real-world problems into machine learning frameworks.
So it's not just about the technical skills.
It's about being able to solve problems in creative ways.
This has been so helpful.
I'm glad you think so.
I feel a lot more confident about exploring machine learning now.
That's great to hear. And remember, there's always more to learn.
Yeah.
Keep exploring, keep experimenting, and keep asking questions.
Okay.
And you'll be amazed at what you can achieve with the power of machine learning.
This deep dive has been awesome.
Glad you liked it.
We've covered so much, from linear regression to all those nuances of classification.
Yeah, a lot of information.
I hope this encourages our listeners to keep learning about this fascinating field.
And for those who want to learn even more, there are tons of resources online.
Yeah, I'm sure.
From open source libraries and tutorials to research papers and online courses.
Right?
The machine learning community is huge and very supportive.
That's good to hear.
So don't be shy. Reach out and connect with other people who are also passionate about this stuff.
That's a good point. The world of machine learning is constantly growing. There's always something new to learn. So keep that curiosity alive, and you never know. You might just make the next big discovery.
You never know. That's right.
Thanks for joining us
Yeah, thanks for having me.
for this deep dive into machine learning.
My pleasure. It was fun.
Until next time.
See you later.